Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind and knowledge becomes a soft lullaby for the night. Tonight's journey will take us into a deceptively simple question. Why is it so incredibly difficult to reach the other planets in our solar system? Even the ones that seem close by, like Mercury or Mars. But before you settle in and get cozy, I'd love if you could take a moment to like this video and subscribe, only if you truly find these quiet explorations enjoyable. And when you're ready, leave a comment to let me know where in the world you're listening from and what time it is for you right now. It's always such a joy to see all the places we gather from, each in our own little slice of time. Now feel free to dim the lights, maybe turn on a fan for a soft background hum, and let's gently begin our journey into the challenges of space travel together. And if your mind begins to wander, that's perfectly fine. Let it drift. We'll still be here, quietly unfolding the story. You might imagine that in a time when we can send high-definition videos across oceans instantly, or fly across continents in mere hours, surely we can hop across the solar system with similar ease. After all, Mercury is just a few dozen million kilometers away. Mars, though farther, still orbits within a manageable distance, close enough that we can see it with backyard telescopes on clear nights. So why does it take years to reach these worlds? Why do missions cost billions of dollars, involve dozens of countries, and require decades of planning for just a few minutes of activity on a distant surface? To understand why, we need to gently peel back the comforting illusion that space is simply empty distance. It's not. Space is vast, yes, but more than that, it's full of invisible challenges. Space is a landscape without roads or rest stops, without air to break in, or fuel stations to recharge. It is a place where motion is constant, but nothing helps you move, where everything is in freefall, all the time. Imagine you're standing on a frozen lake trying to walk to a tree you can see in the distance. Every step you take slips. Every push sends you spinning. There's no friction, no grip. Getting anywhere takes planning, energy, balance. Now replace that lake with a vast silent void, remove the ground beneath your feet, and make every direction just as slippery. That's what it feels like to try and cross the space between planets. And it's not just distance. Planets are moving targets. They're not stationary islands waiting for you to arrive. They whirl around the sun, each on their own elliptical racetrack. So if you want to go from Earth to Mars, for example, you can't just point and shoot. You have to aim where Mars will be months from now, not where it is today. It's a bit like trying to throw a ball at a moving carousel from another spinning carousel. The timing has to be just right, or you'll miss completely. This is why we talk about launch windows, narrow periods of time, sometimes only a few weeks long, when everything aligns just enough to make the trip possible. Miss the window, and you might have to wait over 2 years to try again. Even then, you're not steering like a car, you're falling, gracefully, precisely, into curved trajectories shaped by gravity. We'll talk about those curves later, when we visit the planets one by one. For now, let's stay close to home a little longer. Even escaping Earth isn't simple. Our planet's gravity holds on tight. To break free, a spacecraft needs to accelerate to over 11 kilometers per second, more than 40,000 kilometers per hour. That's not just fast, that's violently, blisteringly fast. And to do that, most of what a rocket carries is more rocket, specifically fuel. In fact, for many missions, more than 90% of the launch mass is fuel needed just to lift the remaining few percent into orbit. Think of it like trying to climb out of a well by building a tower beneath you, but the bricks you build will also weigh you down. Every kilogram of fuel adds weight, requiring even more fuel to lift it. It's a loop of diminishing returns, and engineers have spent decades trying to find clever ways around it. Once you finally get into space, though, things don't suddenly become easier. There's no air to slow you down, which means no air to help you land either. There's no atmosphere to breathe, no pressure to carry heat away, and no magnetic field to protect you from cosmic rays. The vacuum is perfect, and perfectly hostile. Spacecraft have to carry everything they need: air, water, power, shielding, even sometimes their own landing pads. And they must do it without breaking, overheating, freezing, or failing. Every wire, every pipe, every line of software must work flawlessly, often for years at a time, with no repairman just a call away. And perhaps most dauntingly, the farther we go, the more alone we become. Messages take longer to reach us. The sun grows faint. The warmth of Earth fades into cold mathematics and slow calculations. A command sent from Earth to Mars might take 20 minutes to arrive, and another 20 to know if it worked. So tonight, we begin a slow walk through this stillness. We'll visit the planets not as places on a map, but as quiet puzzles, each with their own resistance, their own secrets, their own subtle barriers. One by one, we'll learn why even getting close is a miracle of precision, and why reaching their surfaces remains one of humanity's boldest dreams. But don't worry, we won't rush. There's no need to pack quickly. The stars will wait. Let's begin. Before we even consider setting course for another world, we must first overcome the challenge of leaving our own. It might seem like a small thing. After all, we do it often enough with satellites, astronauts aboard the International Space Station, and probes that have reached the edges of the solar system. But each of these journeys began with a battle, the slow, roaring struggle to escape Earth gravity. You see, gravity doesn't just hold your feet to the ground, it clings to everything, and the deeper you are in a gravitational well, the more energy it takes to climb out of it. Earth, being large and dense, grips us tightly. To leave its surface and enter orbit, a spacecraft must travel at over 28,000 kilometers per hour. And to escape Earth entirely, beyond its gravitational influence, you have to go even faster, about 40,000 kilometers per hour. That's more than 10 times the speed of a bullet. We call this the escape velocity. But even that name is a little misleading, because spacecraft don't just leap into the sky and vanish. They must be guided precisely through a delicate ascent. A typical rocket begins by launching straight up, but very soon it begins to arc sideways, building horizontal velocity to enter a stable orbit. It's not about shooting into space like a cannonball, it's about falling around the Earth fast enough that you never hit the ground. And here's the sobering truth. Most of what a rocket carries isn't payload, it's fuel. Enormous, carefully measured, and violently combustible fuel. The reason is frustratingly simple. To lift something heavy, you need a lot of energy. But fuel itself is heavy. So you need more fuel to lift the fuel, which then requires even more fuel. It becomes a looping dilemma, and solving it is one of the great engineering feats of the modern age. Take the Saturn V rocket, for example, the mighty launch vehicle that carried humans to the moon. Standing taller than a 35-story building, it weighed over 3,000 tons at launch, but only about 45 tons of that, the upper stage and the crew capsule, actually made it into lunar orbit. The rest, mostly fuel. 3/4 of the rocket was burned away just getting the remaining portion out of Earth's grasp. It's a bit like trying to mail a postcard to another continent using a truck that needs a dozen fuel tankers just to cross the street. The proportions are absurd, but that's what it takes to leave a planet with such a deep gravity well. And it's not just the energy, there's heat. As rockets speed through the lower atmosphere, they compress the air in front of them, generating temperatures that would melt steel. The rocket's exterior must endure enormous thermal and structural stress, and once you leave the atmosphere, another challenge begins. The transition to the vacuum of space. The vacuum isn't cold, not exactly. It's not anything, really. There's no air to conduct heat, no water to carry it away. So paradoxically, spacecraft can overheat if they're not carefully designed. There's no breeze in space, only radiation. The side of a spacecraft facing the sun can reach hundreds of degrees Celsius, while the other side freezes. Without a proper thermal control system, electronics can fail, fluids can boil or freeze, and fragile instruments can break down silently, without warning. Then there's the radiation. Earth protects us with a magnetic field and a thick atmosphere, shielding us from cosmic rays and solar flares. But once we cross that invisible boundary into open space, we're exposed. The trip to the moon is relatively short, just a few days. But longer journeys, to Mars for instance, would subject astronauts to months or even years of radiation exposure. Not the kind that gives you superpowers, but the kind that increases cancer risk, damages cells, and quietly wears down the body's internal defences. This is one of the reasons why robotic probes have been our primary explorers so far. They don't need air, food, or shielding from radiation. They don't panic or dream or feel lonely. But even these machines are not immune to the perils of space. Cosmic radiation can flip bits in computer memory, subtly corrupting instructions. A small particle, smaller than a grain of sand, can tear through a spacecraft at thousands of kilometers per hour, leaving behind wreckage invisible to human eyes. So we design redundancies, backup systems for the backup systems, self-checking software, hardened circuits. We send a probe across millions of kilometers, hoping it will survive on its own. Because once it's out there, it's truly on its own. There are no mechanics in space, no rescue missions, no second chances. If something goes wrong, we can only watch, helpless and quiet, as our little emissary drifts into silence. And yet, we do it anyway, over and over again. Every launch is a quiet act of defiance, against gravity, against distance, against the deep, indifferent cold of space. Every mission that leaves Earth is a whisper of hope from a species that once thought the sky was the limit. Still, even as we lift away from Earth, we haven't truly left the hard part behind. Because getting into space is only the beginning. Most interplanetary missions require not just leaving Earth, but entering a carefully planned orbit around the Sun, matching speed and trajectory with another moving world. That means precise navigation, long periods of quiet drifting, and the patience to wait for gravitational windows that open only briefly, then close for years. So before we even talk about landing on Mercury or sending humans to Mars, we must first understand what it means to rise from the ground at all, to slip the bonds of our home planet, however briefly. It is not a small thing. It is not easy. It is not something to take for granted. It is in many ways a miracle every time. And now that we've gently left the surface of Earth, in the next session we'll begin visiting the planets themselves, starting with the one that's closest to the Sun, but strangely one of the most difficult to reach. Yes, we're going to Mercury, but not too fast. Let's drift there gently. Now that we've lifted off from Earth, heavy, rumbling, brilliant, we enter a new kind of silence. The kind that can't be found in a quiet room or a still forest. It's the silence of space itself. A silence that doesn't just mean the absence of noise, but the absence of everything. Air, warmth, friction, pressure. You're no longer surrounded by the familiar blue of sky or the rustle of wind. You've entered the great black ocean above, where the rules are different and every breath depends on a machine that must work perfectly. Imagine floating in a dark lake with no surface, no bottom, and no current to carry you. Nothing around you, not even a whisper. That's the ocean of space. And in that ocean, your ship is not a mighty vessel of steel and strength, but more like a delicate bubble. A pressurized shell, holding in a tiny sliver of Earth, some warmth, some air, some moisture, wrapped in fragile metal walls that separate life from everything else. Spacecraft are often imagined as robust, high-tech fortresses, but in truth, they are more like carefully engineered thermos bottles. Their exteriors must shield against temperature swings more severe than anything on Earth. In low Earth orbit, a spacecraft can move from the blistering heat of direct sunlight, well over 120 degrees Celsius, to the bitter cold of shadow, below minus 150 degrees Celsius in just a few minutes. That's the difference between boiling and freezing in the blink of an eye. But in space, there is no air to carry heat. So these swings aren't just unpleasant, they're physically strange. Heat doesn't blow or swirl, it radiates, and it can only escape by being converted into infrared light and flung into the void. That's why spacecraft have radiators, not for water, but for heat. They glow gently, pushing warmth into space like a whisper from the hull. Inside the spacecraft, the needs are human, but the environment is not. Air must be kept at the right pressure. Oxygen must be constantly recycled. Carbon dioxide must be scrubbed away before it builds up. Humidity must be controlled to keep water from condensing inside electronics. Everything, every breath, every droplet of sweat, every exhalation must be accounted for. To do this, modern space vehicles use what's called an Environmental Control and Life Support System, or ECLSS. It's a bit like carrying an entire miniature Earth ecosystem with you, but there's no soil, no trees, no rivers, just a closed loop of filters, fans, pumps and algorithms, each of them vulnerable in their own way, each essential. Even water becomes a looping story. On the International Space Station, more than 90% of water is reclaimed. That means what you drink today may have been someone else's, breath, sweat, or recycled waste just a few days ago. It's a strange and beautiful idea. Survival as a cycle, sustained by trust in a machine. And yet, as astonishing as it is, the ISS is still close to home. Only about 400 kilometres above Earth, it orbits at a distance less than the length of a drive between two cities. If something goes wrong, help is at least theoretically possible. Supplies can be sent. Astronauts can return in hours. The Earth is always just below, visible through the windows like a glowing safety net. But once you go farther, once you leave the grip of Earth's orbit and drift toward another world, that connection begins to fade. You're no longer just flying, you're falling, curving through the solar system on a trajectory that cannot be stopped or reversed easily. You're on your way, and space is in every direction. Communication, too, becomes a slower conversation. On Earth, we're used to instant messages, real-time chats, a sense of connectedness that transcends geography. But in space, distance stretches time. Light, the fastest thing in the universe, still takes over a second just to get from Earth to the Moon. To Mars, it can take anywhere from 3 to 22 minutes, depending on the orbits. That means a round-trip message could take 40 minutes, long enough for a conversation to become a monologue. For crewed missions, that delay changes everything. There can be no remote control in real time, no last-minute instruction, no quick ask mission control. The spacecraft must think for itself, or the crew must. And that kind of autonomy, technical, emotional and moral, is something we've only begun to explore. Isolation becomes more than just a poetic concept. It becomes real. And it's not just about distance from Earth, but distance from other people, other smells, other sounds. The human brain, finely tuned to social interaction, can begin to unravel without variety. On long-duration missions, astronauts undergo careful psychological screening. They train in underwater habitats or Antarctic stations to simulate the mental toll of confinement. They keep journals, they follow schedules, they talk to therapists through delay-laden video links, because in space, your mind can drift, time can stretch, days and nights blur. The circadian rhythm, your internal clock, loses its natural anchor. On Earth, we reset ourselves by the rising and setting sun. But in orbit, the sun can rise and set every 90 minutes. Or, if you're travelling to Mars, it can hang suspended, unmoving for days. Sleep disorders, mood shifts and emotional fatigue are all quietly waiting in the background. That's why even the soft things matter. A favourite photo, a familiar smell, a recorded voice from home, Small reminders that you're still a person, not just a passenger in a machine. And the machine itself must be perfect. There's no room for error. A single leak, a miscalculation in fuel, a frozen valve, or a misfiring thruster could mean disaster. There's no wind in space to push you back on course. If you drift off, you drift forever. So while space might seem like a smooth emptiness, it is in fact a tightrope walk between precision and fragility. Every moment of survival depends on systems we build, and those systems depend on choices we make, materials we select, redundancies we include. That's what makes interplanetary travel not just a technical challenge, but a human one. We're not just sending probes into space, we're sending hopes, fears, breath, and memory. We're asking a vessel to become a little world of its own, a world that can carry life where no life should be. Next, we'll look toward the first of our planetary destinations, the closest to the Sun, and perhaps the most counterintuitive of all. Mercury awaits. If you were to glance at a simple diagram of the solar system, Mercury might seem like the most convenient planetary neighbour, snuggled right up against the Sun, nearest to Earth in its average proximity. You might picture it as an easy first step outward, a dry rock just waiting to be visited and surveyed. But as with many things in space, closeness is not simplicity, and Mercury, small and fast and sun-scorched, proves that sometimes the nearest things are the hardest to touch. Mercury circles the Sun in just 88 Earth days, racing through space faster than any other planet. Its speed is a consequence of the Sun's immense pull, a gravity well so deep that anything orbiting closely must move swiftly to avoid falling in. And that same gravity, so useful for gaining speed, becomes a quiet menace when your goal is to stop. When a spacecraft travels toward Mercury, it doesn't just fall sunward, it accelerates. The closer it gets to the Sun, the more energy it gains, and paradoxically this makes it harder to slow down. To enter orbit around Mercury, a spacecraft must not only counteract the pull of the Sun, but also cancel out its own momentum. That means expending enormous amounts of fuel, not to go faster, but to go slower, gently enough to be captured by Mercury's tiny gravitational tug, rather than slingshotting past it forever. This is why reaching Mercury isn't simply a matter of pointing and launching. It's a long, spiralling descent, a carefully orchestrated ballet of gravitational assists and measured corrections. The Messenger spacecraft, which successfully orbited Mercury in 2011, spent more than 6.5 years reaching its destination. It didn't take a straight line. It looped around Earth once, around Venus twice, and past Mercury 3 separate times, each flyby acting like a soft tap on the brakes. Only after this patient looping journey did it finally slip into orbit, like a feather falling gently into a deep, silent crater. And once there, the difficulty didn't stop. Mercury's environment is among the harshest in the solar system. It is a world of extremes, with days that last longer than its years. One full rotation of the planet takes 59 Earth days. That means if you stood on the surface and watched the sky, you'd see the Sun rising in slow motion, climbing with unbearable brilliance, pausing, then retreating, before rising again. The Sun appears to reverse its path because of the way Mercury rotates, an optical illusion carved by gravity and orbital resonance. It's a sky that plays tricks with time. Temperatures on Mercury swing from over 430 degrees Celsius in the daytime to minus 180 degrees Celsius at night. That's hotter than a pizza oven and colder than liquid nitrogen, all on the same surface depending on which side is facing the Sun. And unlike Venus or Earth, Mercury has no thick atmosphere to distribute heat, no clouds to shade the surface, no air to whisper warnings. Its silence is not just audible, it's thermal. Landing on such a world requires shielding from one side and insulation on the other. Instruments must be prepared to bake and freeze in rhythmic succession. Solar panels, which are usually the most straightforward energy source for spacecraft, must be carefully angled to avoid overexposure. Even light becomes something dangerous here, intense enough to degrade materials, to cook wires, to flood delicate optics. And because Mercury is so close to the Sun, any spacecraft nearby must contend not only with heat but with radiation. The solar wind, a stream of charged particles flowing outward from the Sun, is more intense here than almost anywhere else in the solar system. Mercury does have a weak magnetic field, surprisingly so for a planet its size, but it's not enough to protect against the steady rain of energy that bathes the space around it. Despite all this, Mercury holds mysteries. It may be small, but it is not simple. Its surface is scarred with vast cliffs, called scarps, hundreds of kilometres long and thousands of metres high. These cliffs formed as the planet cooled and shrank, its crust folding in on itself like a wrinkled apple left in the cold. Some of these features are relatively recent, geologically speaking, suggesting that the planet is still slowly changing, still quietly alive in a way we didn't expect. Messenger taught us much, mapping the surface, studying the chemical composition of rocks, even hinting at the presence of water ice hidden in permanently shadowed craters near the poles. Yes, even on a planet where the daytime heat could melt lead, there are places so cold and dark that ice can persist, untouched, ancient, preserved in silence. And now, another mission is on its way. Bepi Colombo, a joint effort by the European and Japanese space agencies, launched in 2018. It too is taking the long road, using flybys and careful manoeuvres to reach Mercury by 2025. It carries 2 orbiters, one to map the surface, another to study the magnetic field. Together they will explore questions that Messenger left behind. Questions about Mercury's origin, its inner structure, its tenuous exosphere, and its place in the story of our solar system. Because Mercury, though it seems like an afterthought in many planetary discussions, may in fact hold the clues to everything else. It is dense, far denser than it should be. It has a massive iron core suggesting a violent past, perhaps the remains of a planet that was once larger, stripped by colossal impacts or tidal forces. It is a survivor of chaos, a remnant, a scar. And sometimes the smallest things remember the most. So here at the edge of the sun's glare we find our first lesson in interplanetary travel. That closeness does not equal ease, that light can blind as well as guide, and that even the simplest looking world may carry a complexity deeper than we imagined. Our journey continues next to Venus, a world wrapped in clouds, bright and alluring, yet hiding storms that rage forever. But for now, drift a little longer in Mercury's orbit. Let the silence settle around you. Let the sunlight, bright, distant, unreachable, shimmer at the edge of your thoughts. We'll move on soon, but there's no rush. If Mercury teaches us that closeness can be deceptive, then Venus whispers an even stranger lesson, that beauty, even when it shines brightly in the sky, can conceal a world utterly inhospitable to life. You've likely seen Venus without knowing it. It's often the first star to appear after sunset, or the last to fade at dawn, glowing softly near the horizon. The ancients called it both the morning star and the evening star, not realizing it was one and the same, just our neighbouring planet reflecting sunlight with dazzling brilliance. But behind that beautiful shimmer lies one of the most punishing environments in the solar system. Venus is sometimes called Earth's twin, and at first glance the comparison makes sense. It's nearly the same size as Earth. Its gravity is about 90% as strong. It's made of rock, with volcanoes, valleys and mountains that stretch across its surface. If you were to fly past it, without knowing better, you might even think it a familiar kind of place, cloudy, round, and warm. Yet nothing could be further from the truth. The clouds of Venus are not soft carriers of rain, but thick, swirling masses of carbon dioxide and sulfuric acid. They blanket the planet in a permanent haze, reflecting most of the sun's light but trapping even more of its heat. This creates what scientists call a runaway greenhouse effect, an extreme version of what happens in a car left under the summer sun with the windows closed. The result is staggering. Temperatures on Venus reach nearly 460 degrees Celsius, hot enough to melt lead, hot enough to vaporize any spacecraft left unshielded. Unlike Mercury, where the absence of an atmosphere means heat dissipates quickly once the sun sets, Venus keeps its heat like a closed oven. Day and night, pole to pole, the temperature barely changes. It is not just hot. It is relentlessly hot. Everywhere, all the time. And then there's the pressure. The atmosphere on Venus is over 90 times denser than Earth's at sea level. If you were standing on the surface, it would feel like being a kilometre under the ocean. Even the most robust Earth-based submarines would struggle with that kind of force pressing in from all sides. For a spacecraft, it means every landing must contend with not only crushing weight, but the abrasive, corrosive chemistry of sulfur and carbon compounds. Despite these hellish conditions, we've tried to visit. The Soviet Union, during the 1960s through 1980s, launched a series of probes under the Venera program. It was an audacious attempt, one that resulted in many failures, but also moments of quiet triumph. Venera 7 in 1970 became the first spacecraft to transmit data from the surface of another planet. It lasted only 23 minutes. Later missions, like Venera 13, managed to capture and send back colour photographs from the surface, images of cracked orange terrain under a heavy mustard-coloured sky. The rocks looked sharp and dry, scattered across a flat plain. No wind, no water, no life, just heat and silence. And after that, mostly nothing. For decades, the surface of Venus has remained untouched by robotic eyes. The reason is simple, it's just too hard. Most electronics fail within minutes, if not seconds. Even with the best insulation, the ambient temperature overwhelms circuitry. Batteries degrade, cameras fog, motors seize. The thick atmosphere slows descent probes, but once they touch the ground, they have very little time to speak before falling into a terminal silence. Unlike Mars, which we've visited again and again with rovers and orbiters, Venus remains a kind of mystery behind a veil. We know it exists, we see it gleaming in the sky, but its surface is largely unmapped, its geological history only half guessed, and its potential for past oceans or volcanoes still a matter of scientific debate. Even the clouds resist our efforts. Thick and reflective, they hide the surface from view. Ordinary light cannot penetrate them. Only radar imaging, like that used by NASA's Magellan spacecraft in the 1990s, can reveal the contours below. What we see in those images is a world shaped by lava, by tectonics, by something once active. It hints that Venus may not always have been like this. Some models even suggest it might once have had water, perhaps even shallow oceans billions of years ago before runaway heating took hold. If that's true, Venus is not just a hostile planet. It's a lost paradise. A vision of what Earth might have become under different circumstances. A sister who chose another path. And that makes it even more haunting. New missions are now being planned to return to this clouded world. NASA's Veritas and ESA's Envision will orbit Venus in the coming decade, using advanced radar and spectrometry to map the surface, understand its chemistry, and possibly detect signs of recent geological activity. Meanwhile, proposals are being explored for landers that could survive longer, maybe hours, maybe days, by using high-temperature electronics and passive cooling systems. Still, the dream of a Venus rover remains distant, more science fiction than engineering reality, for now. Even dreams of aerial exploration, floating probes that drift in the upper atmosphere where conditions are more Earth-like, remain in early design phases, because Venus, despite its beauty, is like a locked room with fire on the floor and acid in the air, and yet we keep knocking, not because we expect an answer, but because the silence itself is compelling. As we drift away from Venus in our mind spacecraft, we leave behind a place that is close, bright, and yet deeply unreachable. A planet that shines down on us nightly, whispering nothing, wrapped in clouds that no eye can see through unaided. It is a place we thought we understood, then realized we did not. Next, we move toward Mars, fainter, colder, and more promising. The planet of hopes and novels, of rovers and plans. But we won't hurry. There's time. Venus may not invite us in, but she's left a mark on our imagination, a reminder that not all beauty is kind, and not all mysteries are meant to be solved at once. So rest here a while, beneath the sulphur clouds and silent lightning. Let the soft glow of Venus fade behind your eyes, and when you're ready, we'll continue. There is a kind of quiet longing that follows Mars wherever it goes. It is not the brightest planet in the sky, nor the largest. It does not have Venus's glamour or Jupiter's grandeur, and yet, for reasons both practical and poetic, Mars has become our chosen destination, the planet we reach for with stories, with science, and with soft ambition. You've probably heard it called the Red Planet, and from Earth, through a telescope or even with the naked eye on a clear night, it glows with a gentle rust-coloured hue, steady and soft. That colour comes from iron oxide, dust and rock, weathered into a pale, dusty coating over millions of years. But from a distance it looks almost like a blush, a planet caught in a moment of quiet vulnerability. What draws us to Mars is not just its visibility, but its potential. Unlike Venus, whose surface melts metal, or Mercury, which dances too close to the Sun, Mars seems, at least from afar, like a place we could walk on. Its gravity is lower than Earth's, but not too low. It has days that are only slightly longer than ours. It once had flowing water. It still has polar ice, clouds, seasons, and winds that shape its surface. For decades, Mars has whispered that it might, just might, be a second home. But for all its allure, Mars is far from easy. Let's begin with distance. Mars, at its closest approach to Earth, is about 55 million kilometres away. That's roughly 1,000 times farther than the International Space Station. Even with our fastest rockets, the journey takes around 6 to 9 months, depending on orbital alignment, launch windows, and trajectory. And because Earth and Mars move at different speeds around the Sun, the ideal window to launch a mission comes only once every 26 months. If you miss it, you wait over 2 years. Then there's the problem of coming back. A round-trip human mission to Mars would take at least 2.5 years. 6 months there, a year and a half waiting for the planets to realign, and 6 months to return. That's 30 months in deep space, far from Earth's magnetic field, with no easy rescue, no real-time communication, and no second chances. A crew would need to bring everything: food, water, medical supplies, power systems, radiation shielding, life support, spare parts, habitats, tools for repairs, equipment for science, and a vehicle capable of returning them to orbit, and eventually to Earth. And all of that has to be launched into space first. Not in a single rocket, but likely in dozens, assembling it in orbit, piece by piece, before departure. Imagine packing not for a weekend trip, but for a multi-year expedition where every gram of weight matters, and every failure might mean the difference between return and remembrance. And then there's Mars itself. Its atmosphere is present, but just barely. About 1% the pressure of Earth's atmosphere at sea level. That makes it too thin to breathe, too thick to ignore. Parachutes, for example, don't work the way we're used to. They deploy, but they can't slow a spacecraft enough to land safely. That's why Mars landings require combinations of heat shields, retro rockets, inflatable cushions, and even complex crane systems, hovering machines that lower rovers gently onto the surface by cable before flying off and crashing far away. It's a choreography that must unfold flawlessly, often automatically, because by the time the signal from Earth arrives, the landing has already happened, or it hasn't. But even if you land safely, Mars does not welcome you. The surface is cold. Even at the equator, daytime temperatures rarely rise above freezing. Nights plunge far below. Dust storms can last for weeks, sometimes engulfing the entire planet in a reddish haze. These storms can block sunlight for days, starve solar panels, and damage sensitive instruments. The dust itself is fine and pervasive. Electrostatically charged, it clings to everything, finds its way into joints and seals, and might even be toxic if inhaled. Radiation is another challenge. Mars has no global magnetic field to deflect cosmic rays, no thick atmosphere to absorb them. Astronauts would be exposed to levels of radiation far higher than on Earth or even the Moon. Long-term exposure increases the risk of cancer, cardiovascular problems, and damage to the nervous system. Shielding can help, but adds weight. Underground habitats might be necessary. Or perhaps living quarters made from Martian soil, shaped and hardened like adobe in a desert without rain. And then, perhaps most invisibly, there's the human toll. Living on Mars, even temporarily, means living in confinement. No trees, no oceans, no fresh air, no direct view of Earth. Every breath filtered, every meal rationed, every hour scheduled. Time itself begins to shift. Days are slightly longer than on Earth, but not enough to be obvious. Sleep cycles can drift. Isolation can grow. Communication with Earth is delayed by several minutes each way. That means no video calls, no live conversations. Just long pauses between messages, a kind of digital solitude. Psychologically, this isolation is perhaps the hardest to prepare for. Simulations on Earth, in polar stations, submarines or enclosed habitats, offer some insight, but none of them can recreate the silence of another planet, the weight of knowing you are a world away, the absence of blue skies and green life. And yet, we keep planning. Space agencies and private companies alike are designing missions. Prototypes of Martian habitats are being tested. Rovers scout possible landing zones. Instruments search for signs of ancient life, perhaps in dried-up riverbeds or beneath the icy crust of polar caps. Each mission brings us closer. Each one builds on the last. We are not rushing. We are learning. Carefully, slowly, respectfully. Because Mars may be the most wanted destination, but it does not owe us anything. We approach it not as conquerors, but as guests. Tentative, hopeful, aware of the distance between dreaming and doing. So now, let's pause here, at the edge of Mars' atmosphere. Not quite ready to land, but looking down. Through thin clouds and red dust, into canyons and craters, wondering what waits below. We've come a long way, but we still have more to learn. Next, we'll step gently onto the surface, with rovers and wheels and waiting cameras, and we'll see what Mars has already shown us quietly, in snapshots and signals across the stars. Long before we ever dreamed of sending humans to Mars, we sent messengers. Not with wings or scrolls, but with wheels, antennas and solar panels. Tiny travellers carefully constructed on Earth, launched on plumes of fire and cast into the vast silence between planets. These rovers and orbiters have been our eyes and ears on Mars, watching, listening, measuring, and patiently waiting for our questions to reach them, for our commands to arrive across the cosmic delay. It all began with failure. The first attempts in the 1960s, part of the American Mariner series and the Soviet Mars program, were riddled with heartbreak. Probes failed to leave Earth's orbit, lost communication, missed their targets entirely, or crashed silently into the Martian surface. For a while, Mars seemed to resist our efforts, as if testing our patience, asking us whether we were ready to truly try. But with time, success began to unfold, not loudly, not all at once, but in quiet increments. Mariner 4 in 1965 became the first spacecraft to fly by Mars and send back images. They were grainy, black and white, and at first glance disappointing. Just craters, dust, and flat plains. Mars looked less like a second Earth and more like a dead moon. The romance faded briefly, but the questions didn't. Later missions, like Viking 1 and 2 in the 1970s, landed softly and sent back the first colour photographs from the surface. Reddish soil, pink skies, rocks scattered like memories across an empty stage. The Viking landers also conducted biology experiments, searching for signs of life in the soil. The results were strange and ambiguous. Some hinted at chemical reactions that mimicked biology. Others suggested contamination from Earth. In the end, nothing conclusive, and perhaps that uncertainty was even more intriguing. Then came the orbiters: Mars Global Surveyor, Mars Odyssey, Mars Reconnaissance Orbiter. They gave us detailed maps, images of dust devils spiralling across plains, and hints of dark streaks that might, just might, be seasonal flows of salty water. They found ancient river valleys, dried up lake beds, and sediment layers that looked like those on Earth, built by flowing liquid over long spans of time. Mars, it seemed, had not always been dry. Once, perhaps billions of years ago, it may have been wet, warmer and more hospitable. Something changed, something ended, but it is the rovers that have captured most hearts. In 1997, the tiny Sojourner rover rolled onto the Martian surface from the Pathfinder lander. It was no bigger than a microwave, and it didn't travel far, but it proved that we could move on Mars, could drive and explore, even if only by inches. It was the first wheeled emissary on another planet, and though its mission lasted just a few weeks, it opened the path for everything that came after. Spirit and Opportunity arrived in 2004. Twin rovers meant to last 90 days. Spirit endured for over 6 years, exploring craters, climbing hills, and eventually becoming stuck in soft soil, where it continued to send back data until even its silence became a kind of message. Opportunity lasted even longer, 15 years, driving more than 45 kilometres through dust storms and winters, into craters and across plains. When a global dust storm finally silenced it in 2018, NASA sent a final message. My battery is low, and it's getting dark. And with that, a machine became a story, and a story became memory. Curiosity followed in 2012. Larger, nuclear-powered, more ambitious. It carried instruments to analyse rocks, measure radiation, and search for the chemistry of life. It explored Gale Crater, slowly climbing the layered slopes of Mount Sharp, and it found evidence of ancient lakes, complex organic molecules, and environments that long ago might have been habitable, not alive, but friendly to life. A subtle, powerful difference. And now, Perseverance continues that journey. It landed in 2021, carrying with it not just scientific instruments, but something more. Preparation for the future. Perseverance is collecting samples in sealed tubes, which may one day be returned to Earth by a future mission. A true handoff between generations of exploration. It also carried a small helicopter named Ingenuity, a technology demonstrator that proved we can fly in Mars' thin atmosphere, even if only for a few minutes at a time. Every one of these missions has been a whisper into the Martian wind. None have found life, not yet. But each has found signs that life might once have been possible, or that it could still exist, perhaps deep beneath the surface, shielded from radiation, hidden from our orbiters and cameras. But these missions also teach us something about effort, patience, and scale. Landing on Mars is never guaranteed. The process is delicate, complex, and mostly invisible from Earth. It begins with entry into the atmosphere at supersonic speeds, a heat shield glowing white hot. Then parachutes deploy, but as we've seen, the air is too thin to rely on them alone. So thrusters must fire, or retro rockets. Or in the case of Curiosity and Perseverance, a sky crane must lower the rover gently to the ground, then fly itself safely away. NASA calls this process the 7 minutes of terror, but perhaps a softer phrase is more fitting: 7 minutes of silence. Because by the time the signal reaches Earth, it's already over. We don't steer in real time, we only wait and hope. It's a strange kind of exploration, a blend of precision and faith, of mathematics and emotion, of metal and poetry. As of now, Mars has never heard a human footstep, has never felt the weight of a human body, but it has been touched gently by machines we built with care, launched with hope, and guided from a world away. We are learning, slowly, steadily, not with grand leaps, but with patient wheels and cautious landings. We are building the knowledge, the confidence, and the tools to go further, and one day someone may walk where the rovers rolled. They may look out across the plains of Mars and whisper thanks to the tiny explorers who came before. But for now, we stay in orbit, watching, listening, wondering. Jupiter is easy to fall toward, but nearly impossible to survive. That, in essence, captures the paradox of this giant. It welcomes you with open gravity, pulling spacecraft in with a kindness that feels like generosity at first. Its gravitational field is so immense, so wide-reaching, that it has helped more than a few of our robotic explorers on their way outward from Earth. A gravity assist from Jupiter is like a cosmic slingshot, offering speed and direction without asking for fuel in return. But if you get too close, if you drift too deep into the layers of this swirling colossus, the story changes. Gravity becomes weight. Momentum becomes trap. Welcome becomes warning. At first glance, Jupiter looks almost serene. Through a telescope, it appears soft and clouded. A layered world of swirling belts and bands, tinted creams and terracottas, oranges and whites, all moving in slow dance around a gentle axis. The great red spot, an ancient storm larger than Earth, rotates endlessly, a muted eye in the sky, and around it all, a hush of moons and magnetic fields, a halo of radiation, invisible and indifferent. But beneath the beauty is a planet that does not forgive mistakes. Jupiter has no solid surface. What we see, those elegant swirls and spots, is weather, suspended in layers of cloud and gas. As you descend into the atmosphere, there is no line, no edge, no ground. Pressure builds, temperatures rise. Hydrogen, the simplest of all elements, compresses under weight until it behaves more like a liquid and eventually like a metal. If you fell into Jupiter, you would fall forever. Not with a thud, but with compression, until every atom of your being was squeezed into something unrecognizable. And long before that would happen, long before descent became destruction, you'd be torn apart by another invisible hand: radiation. Jupiter's magnetic field is the strongest of any planet in our solar system. It traps particles from the sun, accelerates them, and creates a belt of charged death that makes even the radiation zone around Earth seem like a quiet summer afternoon. These radiation belts are many times more intense than the worst levels recorded during the Chernobyl disaster. Any spacecraft entering this zone must be shielded heavily or suffer electronic failure, data loss, and in some cases total silence. And yet, we have dared to try. In 1995, the Galileo spacecraft, which had orbited Jupiter and its moons for years, released a small probe into the atmosphere. It descended by parachute, passing through clouds of ammonia and water vapour, measuring wind speeds, temperatures, and chemical compositions as it went. It transmitted data for just under an hour. Then, at a depth of about 150 kilometres below the cloud tops, still in what we'd call the upper atmosphere, It was destroyed by pressure and heat. No images, no descent to a surface, just data, numbers, whispers from a place where no light escapes, and then silence. Even orbiting Jupiter is not simple. The radiation environment corrodes instruments. Solar panels degrade faster. Communication must be timed and filtered to reduce interference. When we sent Juno to Jupiter in 2011, it was designed with a specially armoured vault to protect its electronics, and its orbit was chosen to avoid the worst radiation zones. Juno doesn't fly close often. It swoops in, gathers data in bursts, then swings far out again, like a cautious visitor who bows respectfully before backing away. And this behaviour is not cowardice, it is wisdom. Because Jupiter is a planet that cannot be touched. Not in the way we've touched Mars or even the Moon. It cannot be walked on, cannot be landed upon, cannot be gently surveyed. It can only be orbited, admired, studied from a distance, and understood through the veil of its own violence. And yet, we are drawn to it. Perhaps it's the sheer size. Jupiter is more massive than all the other planets combined. If it had been just a little more massive, it might have ignited into a small star. Perhaps it's the role it plays in the solar system, sweeping up comets, shielding inner worlds from some impacts, redirecting others. Or maybe it's something more emotional. Jupiter is a symbol of the unreachable, of power without form, a storm without ground. Its presence has shaped our myths. The Romans named it after the king of their gods. The ancient Chinese called it the year star because its orbit marked time. In astrology, Jupiter is associated with expansion, abundance, and wisdom. In science, it is a puzzle we're still unfolding, and it gives back. That's the strange, generous truth. Though it cannot be landed on, Jupiter offers gravity assist to spacecraft bound for farther reaches. Voyager 1 and 2 used its pull to fling themselves towards Saturn, Uranus, and Neptune. New Horizons borrowed momentum from Jupiter to reach Pluto. In this way, the planet that crushes also carries. The planet that offers no foothold becomes a stepping stone. Perhaps that is Jupiter's role. Not to be reached, but to help us reach farther. Not to be known intimately, but to be understood as a force that both resists and enables exploration. We leave Jupiter now, slowly, quietly. Not because we've finished learning, but because we've accepted its distance. There are worlds we can touch, and there are worlds we must only watch. But just beyond, orbiting in its shadow and swimming through its magnetic tides, are moons. Small worlds, icy and rocky and full of promise. While Jupiter guards its centre, its moons tell different stories. Of warmth beneath ice, of volcanoes in the cold, of seas that never see the sun. They are in many ways what Jupiter is not, and to them we now turn. While Jupiter itself is an unyielding force of gravity, pressure and radiation, a place we cannot touch, its moons are something else entirely. They orbit like quiet companions around the storm, each one a different world, a different whisper of possibility. And among them, some may hold more than just rock and ice, they may hold oceans. And where there are oceans, even hidden and silent, the idea of life begins to shimmer. Let's begin with Europa. At a glance, Europa appears simple, an icy sphere, smooth and pale, streaked with dark cracks like veins beneath a frozen surface. But that simplicity is deceptive. Beneath its outer shell of ice, scientists believe there is an ocean, global, deep and salty. A sea larger than all the oceans of Earth combined, held in place not by warmth from the sun, but by heat generated from below. Europa orbits within, Jupiter's gravity well, caught in a constant push and pull. This tugging creates internal friction, and that friction creates heat. It is the same effect that warms your hands when you rub them together, only on a planetary scale. The ice crust floats atop this hidden ocean like a lid, occasionally cracking as the internal pressure shifts, letting water seep upward and freeze again on the surface. We haven't drilled into that ocean, not yet, but we've seen hints. Plumes of water vapour have been spotted erupting from the surface, venting into space and then falling back down like soft snow. These geysers tell us the ocean is real, that it's active, that something stirs beneath the silence. Could anything live there? We don't know, but the ingredients are intriguing. Liquid water, heat, potential chemistry. On Earth, life has been found deep beneath the oceans near hydrothermal vents, where sunlight never reaches and organisms feed on minerals and chemical reactions instead. If it can happen here, it might happen there. But reaching Europa's ocean is not easy. The surface radiation, courtesy of Jupiter's magnetic field, is intense. Instruments must be shielded. Missions must be brief. And to drill through kilometres of ice, to send a probe swimming through a lightless ocean, that requires a technology we haven't yet built. But we're trying. NASA's upcoming Europa Clipper mission will orbit the Moon, mapping its surface, measuring the thickness of the ice, and scouting places where future landers might go. It's not exploration in the sense of footsteps, but in the sense of knocking gently at the door. Then there is Io, Europa's closest sibling and perhaps its loudest. If Europa is ice and quiet possibility, Io is fire and fury. It is the most volcanically active world in the solar system, its surface constantly reshaped by eruptions, lava flows and sulphurous plains. Bright yellows, reds and blacks stain its terrain like paint flung from a brush. The cause, again, is Jupiter's gravity. Io is pulled and flexed by its orbit, squeezed like a ball of clay, generating intense internal heat. The result is a world in flux. No crater remains for long, no landscape settles. It is a place of constant change, restless and raw. And though it's too harsh for life as we know it, Io teaches us something valuable. That moons are not just passive rocks. They can be geologically alive, driven by forces we once thought belonged only to planets. Ganymedes, in contrast, is quieter. The largest moon in the solar system, even bigger than Mercury, it holds a place of quiet mystery. It has a thin atmosphere, icy plains, and signs of past tectonic activity. But most intriguingly, it has its own magnetic field, the only moon we know of to have one. That's not just unusual, it's extraordinary. It suggests a metallic core convecting and spinning beneath the surface, generating magnetism in the same way Earth does. Magnetic fields help shield against radiation. They shape how particles move, how atmospheres behave. On Ganymede, this field is weak, but it speaks to something complex and deep. Ganymede too may have an underground ocean, layered between rock and ice. And while we've yet to see its plumes or taste its waters, the possibility lingers. Callisto is another of Jupiter's large moons, darker, older and more heavily cratered. It doesn't show signs of recent activity, but it is not without its own whispers. Some models suggest it too may have a buried ocean, held not by tidal heating, but perhaps by radioactive decay or remnant warmth. Its surface is ancient, unchanging, a library of impacts and time, and so, around a planet we cannot land on, we find a suite of moons that may be the most promising places to search for life beyond Earth. Not because they are warm and green, but because they are cold and quiet, and yet still moving, still shifting, still offering clues. Future missions may bring landers, ice-penetrating radar, subsurface probes, tiny robots that can melt their way downward, carrying sensors and cameras, searching not for cities or fossils, but for chemistry, for patterns, for bubbles of methane or strange isotopes, or even, if we're lucky, the twitch of something small swimming in darkness. But even if we never find life, these moons already expand our idea of where life could be. They remind us that the conditions for biology are not limited to Earth-like surfaces with sunlight and air. They might exist beneath shells of ice, in oceans that have never seen a sky. We will go slowly, we will go carefully, because these moons are fragile, untouched, and if something is alive down there, even in the most microscopic way, we owe it our respect. For now, we drift on, past Europa's frozen cracks, past Io's flickering volcanoes, past the magnetic whisper of Ganymede. We carry their stories with us, into the dark towards Saturn, another giant, another ringed world of beauty and distance. But before we cross that gulf, pause a moment longer in orbit. Let the light from Jupiter fall softly on your imagination. Let the silence of the moons echo in your thoughts. Somewhere, deep beneath the ice, something may be moving. And whether it breathes or not, it's already changed how we see our place in the cosmos. From a distance, Saturn is elegance incarnate, a planet encircled by rings so delicate and so bright that they seem more like illusion than matter. Through a telescope, Saturn often stuns even experienced observers. Unlike the faint blur of Uranus or the storm-wrapped Jupiter, Saturn appears composed, balanced, almost sculpted. It is easy to believe, if only for a moment, that this place, this giant of gentle gold, was made not by chance, but with intention. But again, the universe reminds us, beauty is not softness, and Saturn, like all the outer giants, is cold, vast and unforgiving. Yet it welcomes our gaze, and we have gazed. In 2004, after a journey of nearly 7 years, the Cassini spacecraft slipped into orbit around Saturn. What followed was not merely a scientific mission, but a kind of long-distance love affair, an extended, graceful dance between machine and planet. Cassini orbited Saturn for over 13 years, flying past moons, diving through the ring plane, sampling magnetic fields, and capturing images that would astonish not just scientists, but anyone with a sense of wonder. And when its fuel was nearly gone, when there was a chance, however small, that it might crash into and contaminate one of Saturn's icy moons, it was guided into the atmosphere and allowed to fall, not in violence but in purpose, a farewell dive, a final embrace. Its signal faded as it was swallowed by the clouds, disappearing not with a bang, but with a whisper. What made Cassini so special was not just its longevity, but its sensitivity. It showed us that Saturn is not just a planet with rings, it is a system, a world of worlds. Over 80 moons orbit Saturn, some as tiny as city blocks, others the size of Mercury. Some are smooth, some cratered, some fractured like ancient bones. But all exist in a quiet balance around the gas giant, each contributing to the story of what Saturn is. The rings themselves, Saturn's most iconic feature, are not solid. They are made of countless particles of ice and rock, ranging from specks of dust to chunks the size of houses. These pieces orbit in vast sheets, reflecting sunlight like frosted glass. Up close, the rings are not smooth, but braided, rippled, carved with gaps and waves. Some are shaped by the gravity of nearby moons, so-called shepherd moons that pull and sculpt the rings like fingers combing through silk. And yet these rings are thin, astonishingly so. Though they stretch hundreds of thousands of kilometres across, their vertical thickness is rarely more than a kilometre. If Saturn were the size of a basketball, the rings would be thinner than a sheet of paper. That something so grand could be so delicate is one of Saturn's quietest wonders. But Saturn is also distant. So far from the Sun, that light takes more than an hour to arrive. And with distance comes cold. Temperatures on Saturn's cloud tops can reach minus 180 degrees Celsius. Too cold for life as we know it. Too cold for solar panels to function effectively. This is why spacecraft sent to Saturn and beyond must rely on nuclear power, using radioisotope thermoelectric generators, or RTGs. These systems are reliable, but heavy, and expensive. Their presence makes every mission more complex, more limited, and more precious. Saturn, like Jupiter, has no solid surface. Its outer layers are made of hydrogen and helium, with clouds arranged in bands and zones. Its atmosphere is less violently coloured than Jupiter's, more muted, more pastel. But storms still churn, winds still race, and lightning flashes in the dark. Beneath the clouds, pressure builds hydrogen, becomes dense. Temperatures rise. Somewhere far below, though no probe has reached it, we believe there is a core. Perhaps rocky, perhaps icy, perhaps something else entirely. But for now, it remains speculation, wrapped in layers we cannot penetrate. But Saturn's story is not just about the planet, it is about what orbits it. Cassini brought with it a small companion, the Huygens probe, built by the European Space Agency. In 2005, Huygens separated from Cassini and descended through the thick atmosphere of Titan, Saturn's largest moon. It became the first, and so far only probe to land in the outer solar system. What it found was not Earth, but something hauntingly similar. Thick orange skies, mountains, channels carved by liquid, not water but methane and ethane. A landscape sculpted by rain and erosion. A shoreline perhaps. A suggestion of lakes. It was cold, far colder than any place on Earth. But the chemistry was rich. Titan in that moment became more than just a moon. It became a mirror, a dream of Earth in slower motion, with different ingredients and a different sun. And there are other moons. Enceladus, which we'll visit more closely in the next session. Rhea, with its bright surface and possible rings of its own. Mimas, shaped like a tiny Death Star, with a crater that seems too big for its size. Tethys, Dione, Hyperion, all names from myth, all different, all turning slowly in the cold. Saturn is not a place we can visit, not yet. It is too far, too harsh, too immense. But it is a place we can watch, and we have. For decades, we have orbited, measured, admired, and in doing so we have learned that distance does not mean silence, that even in the deep cold, wonder thrives. We now drift farther outward, towards Saturn's most compelling companions, moons with oceans, moons with breath, moons that may, against all odds, whisper something back. But before we go, let us pause in Saturn's shadow, beneath its rings. Let us look upward, through that thin, icy veil, and imagine what lies beyond. There is no rush. Not all oceans lie beneath blue skies. Some are buried in darkness, wrapped in crusts of ice, hidden beneath blankets of clouds so thick that light itself forgets how to shine. And yet, these oceans wait, not silent perhaps, but muffled, waiting for us not to arrive but to listen. Around Saturn, in the deep cold of the outer solar system, two such worlds whisper through the void, Titan and Enceladus. They are moons, yes, but not passive rocks, not relics of formation or debris from ancient collisions. These are active places, living in the slow, quiet sense of planetary time, and in them we see not just the past of our solar system, but maybe its future, and maybe even ourselves. Let us begin with Titan. Titan is the second largest moon in the solar system, larger even than Mercury, but unlike most moons, Titan has an atmosphere, a thick, hazy, golden envelope of nitrogen and methane that wraps the world in permanent twilight. From orbit you cannot see its surface, not directly. The haze blurs everything, like amber glass held too close to the eye. But with radar, with instruments that listen instead of look, the surface emerges, cold, sculpted, familiar. It rains on Titan, but not water. Methane and ethane fall from the sky in slow droplets, pooling into lakes and rivers and seas. These liquids carve shorelines, shape valleys, and gather in basins thousands of kilometres wide. The temperatures are low, so low that water is as hard as rock, and methane flows like water does on Earth. You could, in theory, build a boat on Titan and float across a sea of hydrocarbons, a sea that reflects no stars under a sky that never turns blue. And yet, despite the strangeness, Titan is eerily Earth-like. It has weather, climate, cycles of evaporation and precipitation. Its atmosphere creates dunes, moves clouds, hides storms. It has seasons, long and slow, yes, but real. The patterns we recognise on our own world echo here, at a much lower temperature with a different chemistry, but with the same dance of planetary breath. Beneath the crust, scientists believe there is a hidden ocean, water mixed with ammonia, under layers of ice, kept warm not by sunlight, but by pressure and internal heat. This dual world, liquid on the surface and liquid below, makes Titan one of the most intriguing objects in the solar system. It is both a mirror and a mask, a familiar dream wrapped in unfamiliar chemistry. NASA's Dragonfly mission, planned for the next decade, will explore Titan from the air. Not with a rover, but with a drone. An octocopter capable of hopping from site to site across the landscape, studying prebiotic chemistry, sampling the atmosphere, and searching for signs of complexity in the molecules that make up this alien world. It will be the first time we fly in the skies of another moon, listening not just for life, but for the chemistry that might one day make life possible. And then there is Enceladus. Smaller than Titan by far, barely 500 kilometers across, Enceladus is a tiny moon with a giant secret. In 2005, as Cassini passed by, it saw something unexpected near the South Pole. Plumes, jets of water vapour, ice particles and organic compounds shooting into space from cracks in the surface, like geysers from a frozen sea. These plumes come from beneath the ice. They rise from an ocean that lies below the crust, an ocean of salty water, perhaps in contact with rock at the seafloor. In other words, a place where water, heat, and minerals come together. On Earth, those conditions support life, even in the deepest, darkest places. Cassini flew through those plumes. It sampled them. It found hydrogen, organic molecules, and tiny grains of salt-rich ice. It didn't find life, but it found chemistry. The kind of chemistry that, under the right conditions, could lead to something more. Enceladus is not just a frozen ball with a secret heart. It is a moon that breathes, it vents, it reaches outward. Its surface is constantly renewed by falling snow, tiny particles from the plumes that settle back down. It is bright, almost pure white, reflecting nearly all the sunlight that hits it. It glows like a pearl in Saturn's orbit, cold and clean, and yet, under that cold, something stirs. To land on Enceladus would be to arrive at the source, to place instruments near the fissures known as tiger stripes, to sample the ice directly, to drill, or perhaps not even drill, just scoop the snow and melt it in the palm of science. But landing is difficult. The terrain is uneven. The gravity is low. The power constraints are tight. Solar panels are almost useless this far from the sun, and RTGs, nuclear power sources, are limited in availability and mass. Still, the science community dreams of sample return missions, of cryobots that melt their way into the crust, carrying lights, cameras, and chemical sensors, of hydrophones that listen for currents beneath the ice, of data that might one day whisper yes, not loud, not obvious, but enough. Together, Titan and Enceladus represent a kind of quiet twinship, one vast and thick filled with smog and methane lakes, the other small and bare, sparkling with ice and breath. One is a chemical Earth at minus 180 degrees, the other a cryovolcanic ocean hidden in white. Neither is hospitable in the traditional sense. You could not walk freely on their surfaces, breathe their air, or live without machines. But perhaps life, if it exists or once existed, does not need what we need. Perhaps it thrives in ammonia and darkness. Perhaps it stirs not with sunlight, but with chemistry alone. As we drift past these moons in thought, we are reminded that life, if it is out there, is likely to be strange, quiet, unlike us, and that to find it, we must learn to listen differently, to see the subtle patterns, to read the chemistry of longing. Saturn fades behind us now. The moons grow smaller, the light grows colder, but hope lingers, tucked beneath the ice, waiting. We turn outward once more. Far beyond the warm embrace of the sun, past the grandeur of Saturn's rings and the volcanic tantrums of Jupiter's moons, there spins a pale blue world that does not quite follow the rules. It does not shout for attention with dramatic storms or striking colours. It does not boast with flamboyant rings or headlines of exploration. Instead, Uranus waits quietly, tilted on its side like a forgotten sculpture, whispering mysteries that have lingered in silence for decades. Uranus is an ice giant, not in the way we might imagine a world sculpted entirely of frost and crystal, but in its deep internal makeup, which is dominated not by gas like Jupiter and Saturn, but by heavier elements, water, ammonia, methane. Substances that exist here not as soft liquids or gentle vapours, but as high-pressure, exotic forms of ice and slush, compressed beneath thousands of kilometres of atmosphere. This quiet colossus, 4 times the diameter of Earth, rotates at a staggering 98-degree tilt. Rather than spinning like a top, it rolls around the sun like a slow-turning barrel, its axis pointing nearly horizontally, as if reclining while all the other planets stand upright. This extreme tilt makes Uranus one of the strangest members of our solar system family. Its poles, rather than its equator, take turns facing the sun, which leads to seasons unlike any on Earth. Each hemisphere basks in uninterrupted sunlight for 42 years, then plunges into an equally long night. There is no daily rising and setting of the sun, only decades of still light, followed by decades of shade. It's a kind of seasonal rhythm we can barely comprehend, stretching time out until it loses its familiar edges. No one is entirely sure how Uranus ended up like this. One prevailing theory suggests that, early in its life, the planet was struck by a massive object, perhaps even Earth-sized, tipping it over in a single, silent catastrophe. Unlike more violent collisions that shatter or scatter, this one merely leaned Uranus against the wall of its orbit and left it there, rotating sideways ever since. Stranger still is Uranus's magnetic field, which does not pass cleanly through the centre of the planet like Earth's or Jupiter's. Instead, it is offset and lopsided, tilted at 60 degrees from its axis of rotation and shifted significantly away from the centre. This creates a dynamic and asymmetric magnetosphere, one that wobbles and warps as the planet turns, dipping in and out of alignment with the sun's charged winds. It's as though Uranus's magnetic heart beats with its own rhythm, independent of the world around it. But perhaps the most surprising thing about Uranus is how little we've explored it. In 1986, Voyager 2 passed by, offering us our only close encounter with this distant planet. It took just a few hours to gather what data it could during the flyby, a brief glance, a snapshot, and then Voyager moved on. Since then, Uranus has been left alone, studied only from afar, through telescopes and computer models, like an old letter read again and again with no reply. For nearly 40 years we've seen no new images from its orbit, no new data from its moons, no fresh signs of what lies beneath its cloud tops. This neglect isn't born from lack of interest, but from practical limits. Uranus is distant, almost 3 billion kilometres from Earth, and solar energy there is faint, reduced to a thin whisper of warmth and light. Communication takes hours. Spacecraft must travel for years to reach it, often taking complex gravitational routes through the inner solar system before being slingshot outward. These long journeys require patience, funding, and technology, that must survive deep cold and long silence. And for a long time, the scientific community simply prioritised other targets: Saturn's moons, Mars's soil, Jupiter's storms. But Uranus is beginning to call again, not loudly, not insistently, but with a kind of quiet magnetism. Its strange tilt, its ghostly rings, its icy moons, all of them suggest a world that holds answers not just about itself, but about how planets form and evolve far from their stars. A new flagship mission has been proposed, one that would send an orbiter to Uranus, possibly equipped with atmospheric probes and instruments to study its winds, magnetic fields and internal heat. If launched in the 2030s, such a spacecraft might arrive in the 2040s. It sounds like science fiction, but it's within reach. And for a planet that takes 84 Earth years to orbit the Sun, a few decades is only a heartbeat. The atmosphere of Uranus appears calm, blanketed in pale blue with few visible features. This soft hue comes from methane in the upper atmosphere, which absorbs red light and scatters blue. But beneath this calm exterior, winds blow faster than hurricanes, and storms, though rarely seen, can churn with unexpected violence. The planet emits little internal heat, making it unusually cold, even by the standards of outer worlds. Unlike Jupiter and Saturn, which glow with leftover warmth from their formation, Uranus seems to keep its secrets buried deep, letting very little escape. It is also orbited by a family of moons, each named after characters from Shakespeare and Alexander Pope: Titania, Oberon, Miranda, Ariel. These are not simple stones. Some show signs of geological activity, of past tectonics or resurfacing. Miranda, in particular, appears strangely patched together, its cliffs and valleys looking like puzzle pieces assembled by a half-remembered hand. These moons, icy and cratered, may themselves hold hidden oceans or layered histories. But without close inspection, they remain little more than shadows, promises waiting to be kept. Uranus, in its stillness, offers a different kind of wonder. Not the spectacle of fire or the rush of storms, but the grace of mystery. It is a planet wrapped in cold and time, tipped in posture, waiting for us not to conquer, but to understand. Its silence is not emptiness, it is invitation. And so, as we drift past Uranus on this quiet journey, we do not turn away in haste. We pause, we listen. We remember that not all things worth exploring are loud. Some are sideways, some are slow, some are blue, distant, and waiting. If Uranus is a pale whisper on the edge of familiarity, Neptune is the echo that follows, darker, deeper, and just beyond what we can clearly see. It is the farthest known planet in the solar system, a place where sunlight arrives so weakly it resembles moonlight more than day. And yet, despite its distance and dim glow, Neptune pulses with life. Not life in the biological sense, but in the form of motion, weather, and mystery that refuses to fade. Discovered in 1846, Neptune's existence was first, predicted through mathematics. Astronomers had noticed that Uranus wasn't moving quite as expected, wobbling slightly in its orbit. Those subtle irregularities hinted at the presence of another unseen body exerting a gravitational pull. When Neptune was finally found, it became a triumph not just of observation but of deduction, a reminder that the universe reveals itself not only through light but through logic and patience. In physical form, Neptune resembles Uranus in many ways. Both are classified as ice giants. Both are similar in size and composition, with atmospheres of hydrogen, helium and methane. The methane once again is what gives Neptune its rich blue colour, deeper and more vivid than Uranus's soft cyan. But while Uranus seems subdued, distant in personality as well as in space, Neptune is more dynamic, its atmosphere alive with motion, more restless than we once imagined. When Voyager 2 flew past Neptune in 1989, its final planetary encounter before slipping into interstellar space, it revealed a world of surprising activity. Despite receiving just 1/900th the sunlight that Earth does, Neptune supports the fastest winds recorded in the solar system. Jet streams whip through its atmosphere at speeds of over 2,000 kilometers per hour, carrying clouds of methane ice that swirl and stretch across the planet's deep blue face. Storms form and vanish, including the Great Dark Spot, a swirling vortex the size of Earth that was seen by Voyager and then disappeared just a few years later, replaced by other similar tempests. There is something hauntingly beautiful about this activity, a kind of quiet turbulence in the dark. On Earth, storms feed on warmth. On Neptune, they arise in the cold, powered by internal heat still radiating from the planet's core. Like Saturn and Jupiter, Neptune glows slightly from within, retaining the warmth of its formation. But here, in this far frontier, the glow is barely perceptible, a slow-burning ember beneath a sea of wind-swept blue. Orbiting this dynamic planet is a moon unlike any other, Triton. Triton is large, roughly the size of our moon, but it doesn't behave like a typical satellite. Most moons orbit their planets in the same direction that the planets rotate, pulled into motion by the spinning of the primary. Triton, however, moves in the opposite direction. It travels around Neptune in a retrograde orbit, suggesting that it didn't form there. Instead, scientists believe Triton was a wandering object, perhaps a member of the Kuiper belt, captured by Neptune's gravity long ago. That capture must have been a violent affair. To settle into orbit, Triton would have had to shed enormous energy, possibly by interacting with other moons or debris. The result of this cosmic abduction is a moon that is slowly spiralling inward. In the far future, millions of years from now, it will likely be torn apart by Neptune's gravity, perhaps forming a temporary ring system, like a final exhalation before silence. But for now, Triton remains intact, and it is anything but dead. Voyager 2 revealed that Triton has an icy surface covered in strange textures, cantaloupe terrain, it's sometimes called, due to its bumpy, uneven appearance. It also showed cryovolcanoes, plumes of icy material erupting from below the surface, not in fiery blasts, but as soft geysers of nitrogen and dust. On Triton, volcanoes do not burn, they sigh. The world is geologically active despite the cold, hinting at an internal heat source, and where there is heat beneath ice, the possibility of subsurface oceans begins to emerge. Much like Europa or Enceladus, Triton has become a candidate in the search for life, not life as we picture it, teeming and obvious, but microbial, chemical, hidden in the warmth below the frost. We don't know what lies beneath its crust, but we know enough to want to return. And yet, since Voyager's brief flyby, no mission has come close again. That may soon change. NASA has proposed a future mission, called Neptune Odyssey, or sometimes Triton Hopper, that would return to this distant world. The mission is still in early planning, but it reflects a growing interest in understanding not only Neptune and its moons, but also how ice giants function. These worlds are far more common in the galaxy than gas giants like Jupiter. If we hope to understand exoplanets around other stars, Neptune may hold the keys we've been overlooking. And Neptune itself still holds mysteries. Its magnetic field, like Uranus's, is offset and tilted, suggesting a dynamo deep within that behaves very differently from Earth's. Its internal structure remains uncertain, layered with substances that we know exist, but cannot yet model fully under such pressure. Even its rings, faint, dusty and patchy, challenge our understanding. They are barely there, like whispers of something that might one day become clearer, or fade entirely. The challenge, always, is time. At over 4 billion kilometers away, it takes hours for signals to travel between Earth and Neptune. A spacecraft journey would take more than a decade, And the cold, the radiation, the engineering challenges, they all require patience, precision, and endurance. But perhaps Neptune is not meant to be known quickly. Perhaps its secrets unfold not in flashes, but in layers, like a memory that surfaces slowly over years. As we drift away from Neptune now, its light receding behind us like a soft, distant candle, we are reminded that the edge of the planetary system is not the end of wonder. It is the beginning of something else, something quieter, vaster, and even more patient. For beyond Neptune lies the Kuiper Belt, a ring of icy worlds and distant possibilities, and beyond that, a silence so complete it begins to sound like time itself. If you've ever looked at a snow globe, held it in your hands and gently turned it upside down, you might recall the way the tiny flecks of snow take their time falling, the silence of that motion, the feeling that time is somehow stretching inside the glass. Now imagine placing that globe at the edge of the solar system, far beyond the giants, far beyond the warmth, and letting it drift. That is Pluto. That is the Kuiper Belt. A frozen sea of shadows and secrets, where orbits stretch wide and years unfold so slowly that the sun itself begins to seem like just another star. For much of the 20th century, Pluto held the title of ninth planet. Discovered in 1930 by Clyde Tombaugh, it was welcomed as the final piece in the puzzle of planetary motion. But it didn't quite fit. Its orbit was unusually elliptical, tilted and eccentric. It sometimes came closer to the Sun than Neptune. It was tiny, smaller than Earth's moon, and even its brightness flickered with an odd regularity. Something about Pluto always felt off-kilter, like a character in a story who had wandered in from another tale entirely. And yet, it captured imaginations. Children memorized its name. Space enthusiasts dreamt of visiting, and though it lost its planetary status in 2006, reclassified as a dwarf planet, the fascination never truly faded. Because Pluto wasn't just a number on a list. It was the doorway, the threshold, the first sign that our solar system didn't end with Neptune, but instead opened into something much larger and colder. For years, Pluto remained a blur in our telescopes. We could barely make out its surface. We guessed at its composition: frozen nitrogen, methane, and water ice. We wondered about its strange moon, Charon, nearly half its size, locked in a gravitational embrace so tight that they orbit a common centre in space, not within Pluto itself. They are more like a binary world than a planet and moon, a cosmic duet spinning in perfect balance. Then, in 2006, NASA launched a small, fast probe called New Horizons. Its destination, Pluto. Its mission, a single flyby. The journey would take 9.5 years, with no way to slow down, no time to circle or linger. It was a visit measured in minutes, the kind of encounter one might have on a passing train, just long enough to glimpse a face through a window, just enough to remember it forever. And when New Horizons arrived in 2015, it changed everything. Pluto was not just a rock, it was a world. It had mountains made of water ice, towering like stone against a sky of twilight blue. It had vast plains of frozen nitrogen, carved into cellular patterns that looked like skin seen through a microscope. It had glaciers that flowed, not quickly, but perceptibly. It had haze in the sky. It had signs of possible cryovolcanism, and most astonishingly, it showed geological activity. Not from tidal heating like Europa or Io, not from radioactivity like Earth, but perhaps from some subtle internal mechanism we do not yet understand. And just like that, Pluto was no longer the end of the road. It was the beginning of a new map. Beyond Pluto lies the Kuiper Belt, a vast cold region filled with icy remnants from the formation of the solar system. These are not just leftover rocks. They are ancient archives, preserved in darkness for billions of years. Their orbits are long and strange, Some tilt high above the solar plane, others stretch out in loops that take centuries or even millennia to complete. They are not crowded, but they are there. Dozens, then hundreds, then perhaps thousands. Eris, Makemake, Haumea, other dwarf planets, other stories. The challenge of exploring them is scale. New Horizons travelled for nearly a decade to reach Pluto, and beyond that, every kilometre becomes more expensive, more fuel, more time, more patience. Communication becomes more difficult. The sun grows fainter. Solar panels stop working. Power must come from radioisotope generators, which are heavy and limited, and so, most of these worlds remain distant ideas glowing faintly in telescope images, calling to us with a voice too quiet to answer. Yet. But we dream of going back, not with another flyby, but with an orbiter, something that could study Pluto over weeks, even months, something that could fly past Charon, scan its canyons and cliffs, dip into the shadows of its polar regions, something that could then push outward into the belt, visiting other frozen travellers, one after the next, not rushing, not collecting headlines, just drifting through the farthest frontier, listening. Because there's something else out here, something hard to name. It's not just about geology or chemistry, it's about loneliness, or maybe more precisely solitude. These outer worlds are not dead, they are slow, and slowness, we are learning, is not emptiness. Pluto reminds us that even in the deep freeze, change still happens. It just takes longer. The winds are weaker, the cycles are stretched, but mountains still rise, ice still flows, shadows still shift. These are worlds that operate on different timescales, ones our clocks are not built to keep. And as we leave Pluto behind, watching it fade into a pinprick of light, it's tempting to ask, why do we reach for these places? Why spend decades chasing a frozen moonlet billions of kilometres away? Why strain our eyes to see the faintest flicker? But the answer is gentle, and maybe not even a full sentence. Because we can. Because it's there. Because every time we look farther we find more. Pluto may not be a planet, but it is a world. And out there, in the dim blue hush of the Kuiper Belt, there are more. Waiting in silence, turning slowly, watching the sun grow smaller but never quite disappear. And maybe, just maybe, they're waiting for us to return. At the edge of our solar system, the warmth of the sun begins to fade into something more symbolic than tangible. The orbits grow longer, the light softer, the silence more complete. Voyager 1, launched over 4 decades ago, has now passed into interstellar space, a place that is not truly empty, but so thin, so quiet, that even light seems reluctant to hurry through it. And yet, despite all it has achieved, Voyager is only just beginning the first steps of a journey that, if pointed at the nearest star, would take longer than all of human history combined. That star is Proxima Centauri, the closest to our own sun, nestled just over 4 light-years away. On the scale of the galaxy, it's practically next door. Its dim red glow, invisible to the naked eye, burns steadily in the background of the southern sky, quietly orbited by at least 2 planets, one of which, Proxima b, has intrigued scientists with its Earth-like mass and potentially temperate orbit. It's a place that has captured our imagination, not because we know it well, but because we hardly know it at all. It's near enough to see clearly through our best telescopes, but far enough that getting there remains almost impossibly out of reach. When we say Proxima Centauri is just 4 light-years away, it's easy to forget what that actually means. A light-year is not a time, but a distance, about 9.46 trillion kilometres. Multiply that by 4, and you begin to understand the scale of the challenge. We're not talking about a quick detour or a long road trip. We're speaking of a gulf so vast that even the fastest spacecraft we have ever built, Voyager 1 itself, would take over 76,000 years to arrive. And that's assuming it were even pointed in the right direction, which it isn't. This isn't a matter of mere slowness. It's a fundamental mismatch between the distances written into the structure of the cosmos and the lifespans written into our bodies. Chemical rockets, which have powered every interplanetary mission to date, simply can't close that gap. Even ion propulsion systems, while far more efficient, still fall short by magnitudes. Nuclear thermal propulsion, solar sails, even fusion-based drives. These ideas hold promise, but each is either too undeveloped, too fragile, or still theoretical. The problem isn't just speed, it's sustainability, reliability, and time. And yet, we are not without dreams. One of the boldest proposals for reaching Proxima within a single human lifetime is Breakthrough Starshot, an ambitious project that imagines sending swarms of tiny spacecraft, no bigger than a microchip, across the interstellar gulf, each one attached to a reflective sail no thicker than a strand of hair. These wafer-thin probes would be launched from Earth and then accelerated by ground-based lasers, firing beams of concentrated light, pushing them gradually but persistently to speeds approaching 20% of the speed of light. At that pace, a journey to Proxima Centauri would take just over 20 years. But even in this elegant vision, the difficulties multiply quickly. The laser array needed would have to be one of the most powerful devices ever built, capable of holding focus over vast distances. The probes, light as they are, would have to survive decades of travel through interstellar space, where even microscopic particles could cause catastrophic damage at relativistic speeds. And once they arrived, they would have no way to slow down. They would simply zip past Proxima b in a blink, gathering what data they could during their brief flyby, then transmitting it home over another 4 years. That's the best case scenario, a sliver of insight after decades of engineering, planning and patience, and even that remains far from being realised. No such laser exists yet. No such probe has yet flown, but the ambition endures. Not because we expect to see the results ourselves, but because we are drawn, always, to what lies just beyond reach. Sometimes people ask why we care so much about a planet we may never visit. Why pour time and effort into understanding a star so far away, when there are problems right here on Earth? The answer, gently, is that looking outward reminds us who we are. It is not about escape. It is about perspective, about learning how to be patient in a universe that moves slowly, and how to hope in one that does not promise answers quickly. If we ever did send people to another star, the challenges would increase not linearly, but exponentially. A human crew cannot be packed lightly. They would need life support, radiation shielding, artificial gravity, or the consequences of prolonged weightlessness would be severe. They would need food and water, systems to recycle waste, systems to mend those systems, and perhaps most importantly, systems to maintain their mental health across decades of isolation. The ship would have to be more than a vehicle, it would have to be a world. And yet, even this is not beyond imagination. Some envision generation ships, vast vessels where multiple human lifetimes unfold during the voyage. Others picture cryogenic sleep, slowing biological processes so a person can sleep for decades and wake to a new sky. Still others suggest we send artificial minds, trained to think like us but free from our frailties. Each solution raises more questions than it answers. But none can escape the central truth. The stars are very far away, and we are very small. Still, we reach. We build telescopes to peer at Proxima's light, measuring wobbles and flares and faint shadows that might be cast by orbiting worlds. We listen with radio dishes, not expecting a reply but hoping all the same. We imagine, sketch, simulate, plan. Not because we expect to go next year or next century, but because to wonder is to be alive. Voyager 1, still speeding outward into the night, still transmitting, still listening, carries on board a golden record, a phonograph etched with sounds and images from Earth. meant not just for aliens, but for time itself. It holds greetings in dozens of languages, samples of music and diagrams of who we were when we launched it. It is a letter without an address, sealed in hope. That hope is not foolish. It is not naive. It is the quiet defiance of finitude, a way of saying we may be bound by years, by bodies, by gravity, but our thoughts are not. And so we drift, slowly, quietly, with instruments, with math, with longing. One day the gap may narrow, one day a message may arrive. But for now, the stars remain distant, not because they refuse us, but because they are honest. They remind us that the universe is not shaped for our convenience. It is shaped for wonder. And that is enough. For now. There is a kind of stillness that doesn't come from silence, but from scale. From realizing that the timeline you live on, the one filled with alarms and calendars and appointments, is not the only one. The universe runs on another schedule, one not measured in years or centuries, but in revolutions, orbits, and the cooling of stars. It is a calendar without weeks, a clock without hands. And so, when we talk about reaching the stars, the real problem is not propulsion, not even distance really. It's time. A probe to Proxima Centauri, even travelling at 20% the speed of a light, would take more than 20 years just to get there. Add another 4 years for its signal to return. That's nearly a generation of waiting for a single, fleeting message, for a blurry image, a burst of data, a whisper from the edge. But what if we wanted to go ourselves? Not just instruments, not just cameras, but people with hearts and habits and hopes. To build a ship that carries us through the darkness, not in hours or days, but in decades or even centuries. That's when the questions grow heavier. Because if a mission takes longer than a human life, then who do you send? And why? One answer is to send many. A generational ship, a self-sustaining vessel designed to support entire lifetimes, one after another. A moving world where children are born, grow up, grow old, and are buried, all without ever seeing a sky. A community enclosed in metal, lit by artificial day, guided by computer stars, slowly crossing a gulf so wide that no one on board will ever remember Earth firsthand. The mission becomes more than science. It becomes culture, a society adrift, an ark without a flood. It's an idea that lives in science fiction, but also in science planning. Studies have modelled how many people would be needed to maintain genetic diversity over hundreds of years. How food could be grown in hydroponic farms. How waste could be recycled. How conflict could be managed in a closed environment, year after year, generation after generation. These are not just technical questions, they are deeply human ones. Because on such a ship, memory would begin to shift. Traditions might fade. Myths could form. Earth could become less of a place and more of a story. How long before someone asks, why are we even doing this? How long before the mission, inherited but never chosen, becomes a burden? And yet, we do prepare. We test what we can on Earth, in sealed habitats, in deep bunkers, in polar stations where the night lasts for months. Volunteers live in isolation, without fresh air or sunlight, to simulate what it might be like. They measure stress, cohesion, boredom. They try to keep busy. Some bake bread, some write poems, some just stare at the walls and wait. In one such experiment, a team spent over a year in a simulated Martian base in Hawaii. Outside, the sun rose and set. Weather moved across the landscape. But inside, time became different, slower, stretched, mechanical. Even the meals were controlled. Communication with the outside world was delayed. Everything that arrived came late, and eventually even that became normal. These experiments teach us more than just logistics. They teach us about rhythm, about patience, about what happens to people when time no longer belongs to them. There are other ideas. Some propose putting astronauts in hibernation, slowing metabolism through induced torpor, allowing people to sleep through the decades, waking only upon arrival. The science is still in its infancy. We have put animals into suspended states, but humans are more delicate, more complicated. The body is a system that resists interruption, but perhaps someday we will learn how to whisper it gently to sleep without harm. Others suggest removing people from the equation entirely, not because we are unworthy, but because we are slow. Send artificial intelligence, machines that do not tire, do not age, do not miss the warmth of sunlight. Give them instructions, let them watch and wait and learn. Let them become our eyes across the void. And yet, if they discover something beautiful or strange or living, will they understand it? Will we? There is something unquantifiable about human presence, something in the way we wonder, the way we feel awe, the way we name things not just for classification but for love. A machine can see, but it cannot marvel. A robot can measure, but it does not dream. So we are left with a paradox. To go far, we must wait long. To wait long, we must endure deeply. And to endure, we must hold fast to something larger than comfort or speed. A kind of devotion, perhaps. A kind of faith, not religious, but relational. Faith in continuity. In the idea that what we start, someone else may finish. That a journey can be meaningful even if we are not there at the end. We're not used to this. We live in the pulse of now. Our news cycles refresh in minutes. Our clocks divide the day into hours too small to think in. But the stars, they move slower. They change not with headlines, but with epochs. To walk among them requires surrendering to a different rhythm. Maybe this is what the cosmos asks of us. Not just ingenuity or courage, but patience. The kind that grows quietly. The kind that does not demand reward. The kind that looks into the darkness and still chooses to move forward. Because even if we never touch the stars, ourselves, we're already reaching. Every probe, every telescope, every question, each one a thread stretched out into time waiting for someone someday to find the other end. And maybe, just maybe, they will. It's easy to picture space as a kind of emptiness. A vast, open vacuum where movement is unhindered, where silence reigns, and where reaching another world is only a matter of speed. But space isn't truly empty. It's filled with resistance. Not the kind that blocks your way like a door or a wall, but the kind that slowly wears things down. The kind that waits with quiet patience to test everything you send into it. In that silence, even the smallest miscalculation becomes an echo, a frozen valve, a weak solder, a radio signal that never arrives. Out there, small things become final things. We often talk about space exploration in terms of machines, boosters and rovers, trajectories and thrust. But those are only the visible parts. What exploration really takes, beyond hardware and telemetry, is a soft kind of stubbornness, a willingness to be fragile in a place that does not care. It takes something that can't be built in a lab or printed into a circuit. It takes patience, persistence, and the kind of hope that doesn't mind waiting for years. When we sent rovers to Mars, they took 6 months to arrive. But before that came 6 years of planning, testing, designing, redesigning. Engineers had to simulate descent on a world where parachutes barely work, where dust can blind a camera, where the atmosphere is thick enough to complicate entry, but thin enough to offer no real comfort. Each rover was a little miracle of compromise, a balance of weight, energy and resilience, and not all of them made it. We've lost landers to signal errors, to faulty code, to unexpected weather. One mission was lost because a software team used feet instead of meters. Another vanished into silence after a solar panel failed to unfold. Some made it to the surface, only to be buried under storms, or to bounce a little too hard on unfamiliar ground. These moments don't make headlines for long, but they stay with the people who built them. Not because of failure, but because of effort. Every spacecraft that reaches another world carries more than instruments. It carries years of people's lives, long nights in labs, coffee gone cold, whiteboards covered in equations that no one will remember. And for all that work, there's no guarantee of a result. Sometimes, all you get is a signal that never returns, a light that blinks once, then never again. And yet, we try. We tried on Venus, where the surface is hot enough to melt lead, and the pressure is heavy enough to crush submarines. The Soviet Venera landers made it there. Barely. They survived for minutes. Some managed to send back photos before being overwhelmed. Others just stopped. Their signals, swallowed by a planet that breathed sulfur and heat, became a kind of final heartbeat. And still, we call those missions success stories, because they reached. We tried on Titan, where the sky is orange and the lakes are made of methane. The Huygens lander floated down through clouds, broadcasting all the way, capturing the sound of wind, the texture of the ground, the shape of a new world. It was the first and only landing on a moon of another planet, and it lasted for a few quiet hours before the signal faded. And that was enough, because it meant we could do it. We could touch another sky. We tried on comets, where gravity is so low that you have to harpoon the ground just to stay put. The Philae lander bounced, tumbled, and ended up in a shaded crevice, where its batteries died before it could finish its work. But for a few brief hours it spoke. It told us what it felt. And that was more than anyone expected. These stories don't always end with triumph, but they always begin with something beautiful. The belief that reaching another world is worth it, even if it's hard, even if it's slow, even if we never see it happen. Because the real challenge isn't building engines, it's building for loss. It's knowing that space does not forgive, and choosing to go anyway. It's launching something you've spent a decade designing, knowing it may vanish. It's watching a screen, hour after hour, for a signal that might never come. And still waiting, still listening. And when that signal does arrive, when a rover lands or a probe sends back its first blurry image, there's a kind of silence that follows. Not shock, not celebration, just quiet. As if everyone in the room suddenly realizes what's just happened. A world that has never been touched before has now been touched. A sky that has never known us has now held our machines. And somewhere in that moment, the scale of it all becomes clear. We are not large. We are not fast. We are not made for space. But we are patient. And sometimes that's enough. To visit just one new world, just one, is not a casual thing. It is not a given. It is the result of thousands of hours of careful hands and sleepless minds, of simulations and setbacks and the kind of resilience that does not always get noticed. Each successful mission is not only a scientific achievement, it is an emotional one, a testimony to our willingness to keep trying. And as we look outward, toward moons we might one day walk, toward oceans we might one day stir, we carry this truth with us. Exploration is not something we do because it's easy. We do it because it matters. Not just for data or for pride, but for the quiet knowledge that we're still learning, still reaching, still curious, and that perhaps is the most human thing of all. Somewhere beyond the planets, past the scattered remnants of the Kuiper Belt, beyond even the ghostly reaches of Pluto's orbit, a small spacecraft continues to drift. Voyager 1. No longer powered by rockets or steered by any hand, it moves through the darkness not with urgency but with calm persistence. It doesn't know that we're still listening. It doesn't need to. It simply continues. Its power fades slowly. Its instruments shut down one by one, like lights going out in the rooms of a house where everyone has already gone to bed. But still, it hums. Still it carries our story, etched onto a golden disc, encoded in sounds and images that no one may ever hear. A child laughing, a heartbeat, greetings in languages old and new, a kiss between Earth and the stars. Voyager doesn't ask where it's going. It doesn't demand a destination. It simply goes. It has become not a mission, but a message, a soft declaration. We were here. We looked up. We wondered. And maybe that's enough. Because even if we never touch another star, we have already done something extraordinary. We've stepped beyond our world, not just with machines, but with meaning. We've reached into the void, not to conquer it, but to listen, to send our breath, our music, our thoughts into the long silence. The story we've told tonight is full of distances, from Mercury's searing surface to Titan's methane lakes, from the swirling storms of Jupiter to the slow-turning solitude of Pluto, from Proxima Centauri's faint red glow to the far-off dreams of future sails made of light. We've drifted across deserts of ice and oceans of radiation. We've watched as missions rose, stumbled, endured, and faded. And through it all, one truth has remained constant. The sky has never stopped inviting us. Not with shouts, but with whispers. Not with certainty, but with possibility. And the answer we give, the quiet answer of spacecraft and science, of curiosity and care, is not just a response to a universe. It's a reflection of ourselves. We reach because we feel. We feel because we imagine. And we imagine because we are made not just of atoms, but of stories. Even now, as Voyager slips farther away, becoming a point not just beyond planets, but beyond our solar wind itself, it is still part of us. Like a dream we released into the dark. Like a lullaby still echoing through a nursery long after the child has fallen asleep. It tells no lies. It promises nothing. It simply says, we tried, we reached, we wondered. And that wonder has taken many forms. An orbiter descending through rings of dust. A rover pausing to take a photo of its own tracks in Martian soil. A tiny probe folding its parachute after landing on an alien moon. A telescope capturing light that left its star before our ancestors built pyramids. And behind each of these, people, hands, voices, hopes. Quiet minds that believed the impossible was simply what hadn't been done yet. You don't need to remember every planet we visited tonight. You don't need to memorize which spacecraft did what, or how far a light year is in kilometers. None of that is necessary now. What matters is the feeling, that gentle widening of perspective, that small reminder that you are part of a species that, against all odds, listens to stars. You live on a planet that watches the sky and builds machines to chase it. You are orbiting something gentle, a sun, a thought, a hope. And though the galaxies are vast and the silence is long, the act of reaching, even once, is a lullaby all its own. So sleep now, if you haven't already. Close your eyes and let yourself drift with Voyager. Past Saturn's rings, past Neptune's wind, past Pluto's quiet heart. Let gravity fall away. Let light become soft. Let time slow until it doesn't matter at all. Maybe in your dreams, you'll walk on Europa's ice, or sail through Titan's haze. Maybe you'll land softly on a planet we've not yet found, or float beside a sun so distant it has no name. Or perhaps you'll find yourself simply orbiting nothing at all in peaceful stillness, where there is no need to move. Whatever you dream, let it be gentle. Let it be wide. Let it carry you as far as you need to go and farther still. The stars are not waiting. They are simply there, quiet, beautiful, unconcerned. But we saw them once and we chose to wonder, and so did you. Thank you for being here, for listening, for letting your thoughts drift across the sky for a while. And if you're still awake, know this: the journey isn't over. It never is. The universe continues, slowly, softly, steadily, and you, in your small and meaningful way, are part of it. Sleep well, Voyager. You're orbiting something gentle,